This video uses the results from the previous videos in this series to look at how a free particle moves in the region outside an uncharged rotating black hole described by the Kerr metric. This third video in this series derives the equations of the geodesics for the derivative of the radial coordinate r dot and with the polar angle set to theta equals pi on 2. So we are restricted to the equatorial plane. So what we're looking to find is the form of the derivative of the radial coordinate r dot dr d tau for a massive particle of mass m. Okay, so x dot mu, the notation we're using here is dx mu d tau. Here's our source mass rotating about the vertical axis here, vertical z-axis if you like. We have some mass m over here, which could be anything, a particle of mass, a micromass, kilograms, hundreds, might be tons. It could be a substantial mass, but not equivalent to the source mass, of course. We're talking about something like a freely falling observatory, a freely falling laboratory falling towards the source mass, caught in the geometry of the source mass. The path it follows, x mu is x mu of tau. I'm using the proper time here because it's a massive particle. Sometimes later in the video I'll use lambda instead of tau just to generalize the result for whether we're talking about a photon or a particle with mass. So for a massless particle such as a photon, we can't use proper time tau. And so some later results in this video will be generalized to include all types of particles, massless and massive. So any particle with mass is referred to as a massive particle. All right. At all points on this world line of the particle, we have a tangent. The tangent is a 4 vector, which is the 4 velocity, u mu, dx mu d tau, which is ct dot r dot theta dot phi dot. The dot is simply the derivative of the coordinate with respect to the proper time tau. And then later on at the end of the video, we can generalize that to include photons and massless particles by using the parameter lambda, since we can't use a proper time for a massless particle. Okay, in the first video in this series, we found the expression for the total energy of a particle in its orbit by using its momentum. So we found that the p component of the momentum, ptc, was times the speed of light c, was m on 2, this object here. Okay, these metric terms here, having the t component in them, t coordinate in them, phi dot c, was equal to the negative of the total energy of the particle. Now, by substituting the metric terms, we can see that this total energy, E of the particle in its orbit, is a function of the coordinates r and theta. So if we substitute for the metric here, the Kerr metric, GTT here, GT phi over here, we can see that the total energy of the particle in its orbit is a function of r and theta. All right. But we can also see it's a function too of t dot and phi dot. But particularly we notice r and theta. All right, now t is a function of r, so t dot d tau, okay, is still a function of r, and phi dot is still a function of r too. It tells us the energy of the particle at each and every point in its orbit, so that's what E gives us. Okay, now, having done that, let's now consider an observer at rest at infinity, and such an observer far from the source mass. The Kerr metric asymptotically approaches that of the flat Minkowski spacetime metric, and the fall velocity of an observer here at rest infinitely far or very far, in other words, very far from the source mass, is c0, 0, 0. That's the contravariant components there. All right. But what is the covariant components? What are the covariant components? What is u subscript mu? Okay, well, far from the source, right, the free particle m experiences what is largely completely asymptotically flat space. And so the metric describing that is that of the Minkowski metric in polar coordinates, spherical polar coordinates, plus the time component, the time part here. Okay, but the geometry around and for some distance from the source mass is the Kerr metric here. All right. Now, U mu, subscript mu, the covariant component, is the metric times the contravariant component mu. So we use the metric to lower it, to lower the components, the index of the covariant components. Contravariant components, sorry, my fault, my apologies. Contravariant components here can be lowered using the metric, the appropriate metric term. So UT is GTT UT, and that gives us in flat space, far from the source, we just have minus C0, 0, 0. Remember, this is far, infinitely far from the source, where the mass here is no longer, or is less so affected by the source mass here. Space-time asymptotically approaches that of Minkowski space-time here. And that's why we can use that. So for an observer far from the source, this is their covariant component of their forward velocity. For an observer at rest, hence the spatial components are 0. Now we can use this result to find the total energy of the particle far from the source mass. Now, far from the source mass, we can use this result here. Okay, so the observer has a forward velocity u mu, the particle has momentum p mu, the total energy of the particle, according to the observer, u mu, is minus p mu u mu. Well, we only need to consider the time component here, pt c, and pt is minus m utc. Okay, remember u mu contravariant was c. pt is this object here, which is minus m times ut, because the negative out front here. This negative is necessary in order to make this a positive result. Energy can't be negative, we're having a positive here. And so we have minus m times minus c. Okay, remember this is the covariant one, which is negative. So minus m times minus c gives us a plus, times a c gives us mc squared. So for an observer far from the source at rest, it sees that the particle of mass m has total energy mc squared. It has no kinetic part. Okay. We can now form a ratio between the total energy of the particle in its orbit and the energy of the particle far from the source mass at infinity, and we'll call this epsilon. So epsilon is E, the energy in the orbit, over is the ratio of the energy E in its orbit at any point in its orbit over its energy at infinity, E infinity. And we can write that as E, unknown E, whatever the energy in the orbit is, over its energy far from the source, mc squared. And this will always be equal to or less than 1. At infinity, both these values agree, and so it's epsilon is equal to 1. Now we can use this result to find an expression for the derivative of the radial coordinate r dot. That's just dr d tau. And for a massless particle photon in future videos, we'll use dr d lambda. Okay, so r dot squared, we found this earlier from a previous video, is GRR, contravariant, over m squared times this object here. Remember, h was the angular momentum, E on c was the energy of the particle, okay, in its orbit anywhere, and this is the angular momentum in the phi direction of the particle. Notice there's no theta term here because we're in the equatorial plane. All right, so we have GRR on m squared times all of this. Okay, this minus and this minus will cancel out, and the square of all this will the minus will disappear anyway. Okay, that's what we have. Next bit, just repeating the last line again, so you don't have to commit it to memory. Here it is. All right, let's work with this. What we're going to do now is we're going to remove GRR is delta on r squared, okay, and GTT is 1 on delta times all of that, and GT phi is this object here times E on CH, and then G phi phi contravariant is minus 1 on is plus 1 on delta, 1 minus 2 GM on C squared R times the H squared. Okay, so we substituted in for G phi phi, GTT, GT phi, GTT, and GRR, the metric terms. Okay, so we now have an expression with energy, angular momentum, we have mass, gravitational constant, and the angular momentum per unit mass, A, of the source mass. So next step is that we want to just multiply across by delta. So some deltas disappear here, 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 and we get a delta in the front here. well, next step is expand out that delta here. Remember, it's just a squared plus r squared minus 2gm r on c squared times that. Just expanding all that out. And we're heading for a result which will give us the energy equation, if you like. Anyway, let's keep going with the algebra. I'll get to the interpretation later. So here we go, expanding this out. Here we are. Next line down. Now we're going to multiply through here. We're going to have c squared on r squared. Okay, so c squared on r. There it goes. Now c squared on r squared times r squared is just going to give us that minus c squared. Remember the minus up the front here. Minus a squared c squared on r squared. Okay, then we have over here, first term here, there's an a squared here, all that. Expanding this out gives us this. And let's keep going here, expanding here. And then we have two more terms when we expand out across the parentheses here. There we go, like that. Okay, let's keep going now. Down here, cancel out the c squareds here. Minus c squared, this object here, we can cancel. I've added this factor of c squared on c squared, and it'll actually turn out to be helpful. And it is actually necessary to do so. Okay, it'll come up y shortly. Then, okay, over here, keep going, plus this one doesn't change, and this factor of c squared on c squared. Multiplying c squared on c squared is the same as multiplying by 1, so we haven't changed anything. It's going to be very handy when we put that in here, because this will come out to be our epsilon squared, as you'll see shortly. Then we have this object here, minus this, minus this. Okay, next line down, some things remain. Now here, this e squared on m squared c to the 4 is the same as e on mc squared all squared. And so that gives us epsilon squared. It was that ratio from the previous slide. Times this object here, plus this one, times epsilon squared, because again, we've got an e squared here, and then we have an m squared, and we have a c to the power of 4. So that is e on mc squared, all squared. Okay, same thing. And the same reason over here, we'll get an epsilon squared plus c minus this. This e on m c squared will give us e on mc squared is epsilon, and then we'll still have an m and a c underneath. Here we go. Plus this object here unchanged, this one unchanged. So if you have a look here, some things are going to cancel out shortly. Okay, let's keep going here. All of this. Keep expanding, keep following through. This here is just the previous line repeated again, just so you don't have to flick back to the past screen. I'll put it up here. Okay, let's go across here. Let's collect some things. Epsilon squared, c squared minus c squared, or they're constants. They look like they sort of go here together, don't they? 2gm on r plus epsilon squared. This bit here, this thing, well, it looks like we could factor something there. Minus this, plus this. Okay, so let's take out a factor of c squared here, put it over here, 2gm on r. Over here we have the r squared terms, r squared, and r squared. There's 3 of them here. And if we introduce a common factor of m squared, so we have a common denominator of m squared, r squared, then that means we have to make some adjustments up here. Gives us this. And same over here, then we pick up all the r cubed terms together, r cubed, r cubed, r cubed. Let's combine those and put them over a common denominator of c squared, r cubed, m squared. So c squared, r cubed, m squared. And then here we need another m, and we need another c here, and then up top as well. And down here we need to write m squared, c squared, and up the top as well. And when we do that, we produce this object here. We can keep going down. Next line, factorize a bit. They're already done. And then from here, we're going to take out the common factor of m squared, a squared, c squared, outside of epsilon squared minus 1, and then minus h squared over that. Same down here, a little bit of factorizing. Here, common factor 2gm all across the top here gives us this over that. Let's just keep going. All right, repeating that last line again. Here it is. That's that last line we just looked at. And next line down, we can write that as this plus this. This bit here is already done. And then here we can factorize this as being in the parentheses here as being h minus am c epsilon all squared over that common factor. So finally we have r dot squared. We could think of this as the kinetic energy per unit of mass, m. This is our particle that's falling in this Kerr geometry. Remember, it could be our laboratory and it's falling towards this rotating source mass. And so we have this here. Okay, here we go. Now that's looking a bit like total energy and some sort of potential-like term. So we can rewrite this in terms of the particle's mass. So I'm going to put a half m r squared here, multiply through by a half and m. We get this object here. Okay. So that's looking like a kinetic energy term here, total energy, and a sort of potential-like term here. Now I'm going to qualify that shortly. So rearranging gives this minus this is equal to this, and we can see that's the kinetic energy plus a sort of potential energy term is equal to total energy. Now, I say potential like, what this is called, this is referred to as the effective potential. It is not a potential energy term. It is a term that behaves something like a potential energy term. That's why it's not just called potential energy, it's called the effective potential. All right. Now the effective potential is given by, if I just take out that part there, Vf is all of this. That's the effective potential. Remember, in Newtonian mechanics, we just had the leading term here. Okay, but in general relativity, we have these corrections here. All right. Now, the effective potential term is not a potential energy term, but it does act, so to speak, like one. Okay, now it cannot be a potential energy term because that would imply the existence of a gravitational force which would be equal to the negative gradient of the potential. So we'd be claiming if this was a potential energy term, if that's what we're saying, then the negative gradient of that would be the force, the gravitational force. Now, this is simply not true in general relativity. There's no such thing as a force. Matter and energy respond to the curvature of space-time and not some force. So the behavior of objects, the dynamics that affect objects is not due to a force. Matter and energy respond to the curvature of space-time. There are no forces acting, and so there's no potential energy. All right, there's no potential energy in general relativity. But there is this term which is potential energy like. It's the effective potential energy. It does act like one, but it's not a potential energy because that would imply the existence of a force, and forces play no part here in the motion of a freely falling object. So gravitational energy does not exist in GR because the equivalence principle says that there is always a local inertial frame. So pick any point in the space-time, there's a local inertial frame, the freely falling one in this case. So you can imagine observers in the laboratory. The laboratory is freely falling towards the source mass, and we could use the walls and the corners of the walls to set up our axes, and that could be our reference point, and make all our measurements from there. In a freely falling frame, right, there's a local inertial frame, and that's the freely falling one, in which space-time is or looks like the flat one of special relativity. So no forces are acting because there is no curvature. In this local freely falling frame, this local inertial frame, there is locally, not globally, but locally, just for a small region around the laboratory, small region of space-time around the laboratory, space-time looks like that of flat Minkowski space-time. So there's no forces acting. Okay, that's what the equivalence principle tells us. There's no curvature, so there's no forces. If there was some form of gravitational energy tensor, reference frame independent, then that tensor would be zero in the frame of SR described above. Okay, because as I said, there's no gravitational force acting, so there's no gravitational energy involved in that freely falling frame, that freely falling locally inertial frame. It would be zero in the frame described above, which also means because it is a tensor, it is zero in all reference frames because it's a tensor. So if a tensor is zero in one frame, then it is because tensors are coordinate independent, then what is 0 in one reference frame must be 0 in all other reference frames. Okay, so if there was some form of gravitational energy tensor, then that tensor would be 0 in the frame mentioned above, and the Minkowski-like freely falling reference frame above, that local inertial frame in other words. And so if its gravitational energy tensor is 0 in that frame, it has to be 0 in every other frame. Okay, so there's no gravitational force, gravitational energy acting. All right, now we can use the effective potential to find the radial acceleration of the particle. Okay, so we have dd lambda. Now this is, I'm generalizing this now, so because this applies equally to massless particles as to massive particles. Okay, so dd lambda, but just think for a massive particle, replace lambda with a proper time tau. So it's, here we go. So we take derivative with respect to the parameter lambda, which for a massive particle is going to be the proper time. And we have dd lambda of all this. Okay, so dd lambda of half m r dot squared, dd lambda of this effective potential term, and dd lambda of the total energy on the right. Okay, so when we do that, well, on the right, the constants there went to 0, they disappeared. And now we do use a chain rule here, so we have 2 times the half times m times dr d lambda. So 2 times the half times m times r dot times dr dot d lambda. Here we go, like that. And the same here, we're going to differentiate again. Gmm on r squared goes from minus to plus as we go from r minus 1 to r minus 2 times dr d lambda minus 2 times all of this, okay, times dr d lambda, and this becomes 2m r cubed, and that plus went to a minus. And then over here, this power is going to increase by 1 to 4, and this will go from minus to plus. And because there's a 3 here, it'll come out front. We'll end up with a 3 here, just as we've got a 2 over here, times dr d lambda. Okay, now we've got m r dot r double dot, dr dot d lambda is r double dot, plus, and I'll rewrite dr d lambda as r dot, r dot, r dot. Now every term has got an r dot in it, so we can divide through by r dot, which is dr d lambda, sorry, and we're left with mr double dot plus this is equal to 0. All right, and sorry, that 2 and that 2 cancelled out. I should have mentioned that earlier. That's why it's not appearing here or here. Okay, and that's all equal to 0. And then we can rearrange that by taking term 2, 3, and 4 over to the other side, leaving the first term by itself, and we get an expression for the acceleration of the laboratory, massive particle, whatever it is, observer, spaceship, whatever. mr double dot is this, okay, and that is equal to the negative of the total derivative of the ordinary derivative of the effective potential with respect to r, the ordinary derivative with respect to r, the effective potential. Okay, and that's it.